Hello everyone, and welcome to the Summer DLAB lecture series this year. We're very happy to welcome Shajay Bhooshan for our first lecture. And well, we've known each other for a very long time. And Shajay is a studio master in Design Research Lab graduate program at the AA, and he's also the co-founder of Zaha Hadid Architects computational research team, CODE. And he has completed his MPhil in 2016 in University of Bath, and now he's working towards his PhD in ETH Zurich. And Shajay has great expertise in several ranges of subjects touching on computation, programming, mathematics, geometry, rationalization, optimization, as well as advanced fabrication. So please allow me to say welcome to Shajay, and we look forward to hearing his research.
Yeah, thank you, Elif, and thank you for being accommodating for the slight earlier start to a lecture series. And thanks also for the invitation. As Elif mentioned, we studied together, so we kind of really know each other for a long time. And so there's been like parts of our careers that like have had synergetic synergies, let's say. So today I'll focus, because it is the DLAB, of course I will focus more on the digital design and fabrication aspects, but I would just like to start off by giving it a little bit of a context, at least the way we approach it in CODE and also in Zaha, and further into our collaborative networks and so on. This particular essay resonates a lot with me, and like in general, I think it should resonate with like most people who have been involved in kind of technical research for a while. Because on the face of it, it sounds like we have to educate our clients and just tell them how things are produced. But the essay actually means a whole lot more. Like it kind of suggests more participation, trying to bring users to get them to participate in the design process, get them to participate in what is actually produced. So it's not like empty words or like flowery words to try and sell whatever you design to the consumer, but like to make a consumer active part in what is produced. And Walter Benjamin wrote this in 1934, and it was in the context of like literary work, comparing like novels with like newspapers. But I think it's as applicable to digital design and fabrication today, because we are in similar crossroads. So there's been extensive amount of research, like perhaps accelerated in the last decade or so, on this topic of digital design and fabrication, and CODE is part of this community, and so a large part of what we do is indeed research. But we also do an equal part applied projects, try to push boundaries like one step at a time. We also increasingly partake or participate in exhibitions and in communicating what it is that we do, and like trying to get feedback into our design processes. And lastly, we also develop kind of in-house talent. Like it's not that we just hire specialists. We are a bit like a Barcelona football club in that sense. Like we try to nurture and grow talent in-house, and also nurture and grow our collaborative network, because a research team or any architectural team is only as good as its collaborative network. So of these, like, I will only speak about the research part, like, and a little bit about the projects. I mean, through the projects, I will talk a bit about the research. And for the last bit, like, there is a small exhibition that's opening in the building center, like just 5 minutes from here. Those of you interested, or those of you still interested at the end of my talk, you can go take a look. So as I mentioned, like a large part of the last decade that the code team has been active, like we have focused, like many other colleagues and extended networks, mostly on the production aspects, the physical aspects, the scientific aspects, and so on and so forth, which most of you would be very familiar with since you're here doing the DLAB. And it's also technological and very in-depth in that sense. But of late, like we are also realizing, along with like the rest of the fraternity, in the sense that like it's about time to ask where does all of this lead to? What can we do already with like this increasing rate of extraordinary progress that the profession and discipline has made? So in that sense, again, like the essay, as I mentioned, like resonates a lot, because we're beginning to think like, you know, how do people consume architecture? And can we incorporate that in the way we produce? Or can we utilize all our research in the production aspects to address some of the opportunities that lie in bringing users into the design process and production process? So there is this kind of slight tension between the production aspects, the physical and the science, with the social and the storytelling aspects, and so on and so forth. So, and we actively aim to suppress technology in whatever we produce, meaning like there's a lot of technology that goes into it, but like at the outside, we're not actively talking about it anymore. So in that sense, all my affiliations are kind of not by chance, it's by deliberate consideration that like half of my affiliations are in the design world and the other is more in the kind of, let's say, research and scientific, or research in the more narrow scientific sense. So what other disciplines and professions actually do this dichotomy or manage this dichotomy very well? Computer graphics and animations are perhaps the most beautiful and clear example of this, because like when we look at a movie, whether it's animated or not, there by now in 2018 there's a lot of technology, not only in the camera but also in the direction and in the all the digital technology that goes into making a movie is extraordinary. Like it's perhaps even more than most buildings, and it also it's cumulative. Like so when you look at Snow or other movies, like you're not like really thinking about like, you know, the physics of Snow and like all the hundreds of researchers and mathematicians and like others who have like slaved over all the technical aspects. Closer to architecture, like it's again not new, like in the 17th, 18th century, like perhaps best exemplified by like Gaudi, like there was lots and lots of fabrication aspects, there are lots of structural aspects that went into the work of Gaudi and his contemporaries. Again, he didn't invent like most of these, it's cultural evolution that like he had access to like ways to calculate structural behavior just through geometry and geometric calculations, like the drawings on my left show. But when it was about making the building, it wasn't about like how things were fabricated. That was only a part of it, right? Like there was like a lot more to Sagrada Familia than like the cleverness in like cutting stone or the cleverness in arranging stone in a structurally meaningful and structurally efficient way. So. And the same can be said about like the other 20th century phenomena of like the Maison Domino and like how it's like spread through all our cities. It's not only because you know, Corbusier came up with this diagram like and kind of made it accessible to a lot wider audience, but also because it went hand in hand with like technological progress, the trade schools, new ways to calculate behavior, and new materials like reinforced concrete, and like new patents and how to use concrete along with like reinforcement. Like, so all of this was like exciting new world in the 20th century. The same way we are like super excited about like robots and AI and data and geometry and form finding and so on and so forth. So it's helpful to look back into history and see how these two aspects like kind of go hand in hand, especially in architecture. One couple like that has like a profound influence or serve as a constant inspiration are the Eames couple. The Eameses, Ray and Charles Eames, like they had like a prolific 80 odd years of career, and they also started somehow in this way. Like they bought this patent of like forming wood from the U.S. Army, set up a company, got the machine into their living room, and then the rest is history. Now Eames chairs like sell all over the world like for incredible amounts of money. And but they were also one of the earliest investors or pioneers from the design world to invest time and effort and develop collaborations in the use of software, like particularly Mathematica, and also production processes, exactly the same way we're doing now in the 21st century. And again, this diagram is from the Eames. What that means is like at the top, at the very top is what they were looking for, a vocabulary, a design language that relates to materials and technique. So in other words, it is like kind of, like if you add digital to that, it is digital design and fabrication. But they were also quickly to understand that like that you have to follow that up with like understanding the social part, like how families behave, or how people interact in communities and so on and so forth. You also have to consider production systems, economics, financing, servicing, and so on and so forth. Like, so, and what's very interesting for us is like their career, like, kind of ended up in like looking at houses and like how people use. They only made one house, but their ideas, like, kind of were more profoundly influencing the entire case study house movement. So that's the kind of backdrop to the presentation, like this idea that like we're spent like the first 8 odd years like looking at developing our language, a digital design and fabrication language, a vocabulary of materials, techniques, and now we're like adding to that, or attempting to add to that, like a social understanding and utilize our already rehearsed language to address like some more social opportunities and community building opportunities. So as I said, I will only touch upon the social part like towards the very end. Like most of the presentation is indeed about the physical aspects, the research aspects, and particularly about geometry, and how geometry can be a common tool, a common way to many people to collaborate, compared to, like, let's say, more numerical studies that a very handful of people can understand. Geometry and physical things, like, a lot of us can understand intuitively and therefore contribute collectively to the design process and also to what is actually eventually produced. So there is idea that we can draw from history, so it's in that sense cumulative, and idea that we can draw from many different disciplines. In that sense, it's it's collaborative. And ultimately, we are adding the term architectural geometry, architectural to the idea of geometry, because it will be physically realized, unlike several other geometric aspects, which are more mathematical in that sense. Just a brief, again, like a background, like in the 20th century, like there were like increasing use of NURBS borrowed from the automobile industry. And as most of you will know, like there are 3 major ways to represent geometry on a computer: NURBS, meshes, and images. And NURBS comes from the automobile and like the aviation industry, and like architecture also inherited this from that industry predominantly in the 20th century and the late 20th century. There were like many buildings, and perhaps the early success and of Rhino, for example, it was based on that paradigm of using NURBS a lot. Like, but most of our work borrows from the computer graphics community, the movie industry, and we use meshes almost exclusively, but not entirely true. But like, let's say predominantly we use meshes. We're also increasingly looking at like image-based ways to represent geometry. Why? Because like images are easy, capture a lot more detail. Like, so you've never heard of a CAT scan that is like represented as NURBS. Why? Because human bodies and other things are not just smooth objects. They have a lot of detail, and like, so images in that sense are. And you can also consider hybrids, but like for the sake of this presentation, let's say most of the work that I will show will fall into these, predominantly the mesh representation, and also a little bit in the image representation. So why use meshes, for example? Well, because it's fun. These kind of things, like that's one of the reasons like computer graphics like really fascinates me and a lot of the people in the team. Is because like geometry and math and programming can really be fun. And as soon as you can like leverage and understand what's going on, you can like then, you know, use it for less, like more boring applications like architecture. Like here, facade optimization and like paneling and blah, 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 like curvature-based paneling in this sense. And also to make sure all the panels are then like flat and like you can join them all nicely together, and like you can bolt them together so there's not twisted. So all of these things are enabled because you're using meshes and because we are borrowing like stuff that's like 30 to 40 years old in many cases. And some are like literally released like 2 weeks ago, like in a different community, so we just have to borrow and make it our own. So and that's how, like, you know, we view complex geometry, like not as something that needs to be optimized and rational. Like complex is actually good because curvature is good in more cases than not. Like curvature is better than flat, and so how do we leverage new ways of making to actually physically produce that curvature? So again, we're borrowing a lot of the technologies and terminology from the computer graphics industry, and particularly when it comes to use of meshes. And so hopefully, like buildings like these, or at least sculptures like these, get built. And again, I won't go too much into the boring technical aspects, just to say that like we're not alone in this, and we're not pioneering anything other than like just looking into the right places and making and forging the right connections. So all these research groups across the world, like from Carnegie Mellon to TU Vienna, and like in Asia and in Tokyo and so on and so forth, are using meshes. Like when it's coming to the production of buildings, they're beginning to use meshes in conjunction with NURBS. So like, why not join them and begin to utilize a lot of the emerging research. And so again, the term architectural geometry is just using meshes that are aware of how they stand up, i.e. they're aware of gravity, and also they're aware of like how they might be physically realized. So it's not some arbitrary curvy geometry that has no idea of gravity or no idea of how it will eventually. So geometry, which is like a designer's problem, is architectural geometry. If geometry you allow the engineer to rationalize for you, then that's not architectural geometry. That's just geometry that someone's having fun with. At least that's our definition. So we want to collaborate with like all these people and all of this extensive emerging knowledge, and that's another reason to look at meshes. Leading research organization like the one where I'm doing my PhD at is like also like you might already be using Rhino Vault and Karamba and like whatnot. They're all mesh-based technology. So you can actually begin to see that, like, you know, lots of researchers, like with 10 plus years of funding, they're looking at investing heavily into meshes. So it's only a matter of time when this becomes more mainstream in architecture. And also, like, you know, pioneering engineers are like advocating the use of this, like Hanif Kara. I don't know how many of you know, he was one of the founders of AKT that helped Zaha Hadid Architects like realize several seminal buildings. Interestingly, also people from other disciplines who are now coming into architecture, like this guy, Mark Pauli, is like one of the exceptional geniuses, let's say. He sold FaceTime to Apple, and now he's interested in architecture. Don't ask me why, but he's also like interested in augmenting meshes with like fabrication related information, structure-related information, environment-related information, like aesthetic information, like curvature flow, and so on and so forth. And of course, these two guys, like you, I'm sure all of you know, and they're also beginning to switch to use of meshes and mesh-based technologies. And also their demonstrator projects, like when these kind of stunning prototypes, I mean, they're soon to become buildings. This was first one was in 2016 in the Venice Biennale, and the next one was in 2017, and so you can like just join the dots and we can see in the next 5 years where things are gonna go. But for us, like what's really important is not so much the technology alone. Like we really want to understand the technology, but what we want to really do is to explore the space of solutions. Like all of these solutions here are like valid in some way or the other for certain structural conditions. But what we see here is this universe of possibilities. So design then becomes like, how do you search through the space for the more appropriate one for your given set of constraints, for your given set of opportunities, and so on and so forth. So the images on my right, like it's from my PhD advisor's PhD, Philippe Bloch, and they're all compression-only geometries, i.e. different kinds of domes and vaults. So you can produce all of these with just brick. And the more tensile ones, I'm sure all of you recognize, they're from the engineers of Reotto in 1960s, from one of the first computer programs that was used to do form finding. They also came up with the math behind it and so on and so forth. So they're called Linkwitz and Scheck. And so to this day, like their method forms the basis for a lot of the form finding that like you might do using like Kangaroo or Rhino Vault. And so underlying that, the numerical method is from the 1960s, 1970s, sorry. Okay, so to that end, like what do we do with that? Like, so the gist of it is geometry, like the main action or the main strategy to address structural and fabrication constraints is to basically move the points of a mesh until certain geometric conditions are met. For example, if you want to stretch fabric, all parts will have like negative curvature, or zero mean curvature, let's say minimal surfaces, so which means like you move the points until that curvature condition is satisfied, and if you want to make it out of paper and things, you move the points again in a slightly different way until it becomes, you know, a certain Gaussian curvature is minimal. So the main takeaway here is that like you move points until you are satisfied, and how you define satisfaction is the key strategy. So, well, for example, with shell structures, like which we have kind of invested an early part of the team's efforts into, here's like something in action. Like this was from like 2007 or 8 or something, but you can see that like the user manipulates or the designer manipulates like a kind of cage geometry, and behind the scenes like these points are being moved almost real time, so you can see. So that's that's one example of like moving points until certain curvature conditions are met, or structural conditions, or environmental conditions, so on and so forth. This is the usual strategy. Having done so, like it becomes very easy to produce. Why did we move those points in that particular way? Because we could then describe the same piece of geometry on site physically by just stretching fabric along the rails. So then there is like a physical meaning, a fabrication meaning to the geometry, and that's like one of the aspects of architectural geometry, is that like that geometry is aware of how it will be made, and it's aware of how the forces affect it, let's say. And the last person on in this series, like I would totally recommend you to to watch that. It's called Geometry and Structure. Like Chris Williams, who was like a professor, who was a professor in Bath, like, and one of the pioneers who helped Foster and Partners build the British Museum library when Karamba and all of these software wasn't available. Like he wrote a piece of software to enable, and it was only a 200 kilobyte piece of software, but like you can see the impact it's had on the profession. Like not only the British Museum, and then like 15 years later, there's like King's Cross Station, and then there's a resurgence of shell structures everywhere, is because of pioneering efforts like Chris Williams and others, like other research organizations that are pushing this paradigm. Anyway, so for us it was like very simple. Like, so once you generate that geometry that way, you just unfold it, cut up the panels, give it to a tailor. They stretch it. He brought the fabric on site, and then we stretch the fabric across the pipes, which are also manually bent. Again, how do you make sure that the pipe is bendable? You move the points of the curve until certain curvature conditions are met, that it is only singly curved, or all the arcs lie on a plane, and so on and so forth. So this moving points is the key strategy no matter what you do. And so, and then like you just stretch the fabric and then put concrete on it, and this was like done already several years ago with with hardly any digital fabrication. Almost all of this was manual, but like we still think this is a very useful example, like that you can use digital tools in proactive ways. You don't necessarily need to be only in a high-tech environment to actually deliver these complex geometries. And this was in India, like in 2009 or something. And again, made with like a handful of labor and over like just 10 days. And you can also, it's also very scalable. That's one of the key aspects of like parametric design or digital design, is that like once you can make something at a smaller scale, you can literally do the same at in a much larger scale. Here, the pipe is of course bent in a more professional, more engineered way, and everything is more calculated, but like the principle remains the same. You just bend pipe and stretch fabric, and then you have a restaurant underneath. This building opened, I think, in 2014. It's Zaha Hadid Architects in the Serpentine, extension to the Sackler Gallery. Again, so geometry is key, but like, and why is geometry key here? Like these if someone told you that this is entirely compression, meaning you can make this curvy geometry entirely stand without any glue and without any reinforcement, like only in stone, you wouldn't probably believe it. But what's important here is that like this, and all the importance of Philippe Bloch and his PhD and the research of Bloch Research Group is trying to open up like this numerical calculation to kind of geometric intuition. Like, so the bottom right diagram already tells you the forces, if you know how to read it, tells you the forces that are going to be active in the geometry. And how do you get that diagram? That's also very clever. It's purely by construction. You just take the geometry that is projected down and rotate all the edges. And then you already get that. And of course, there's some numerical aspects, but like, because a lot of this is like geometric operations, it becomes more accessible to designers, and so at least that's why what originally fascinated me about Philippe's work was the geometric nature of that entire field. It's called graphic statics, and it's again not invented in the 20th century. It's like goes all the way back to Newton and others who use geometry to do some of their physics aspects. Okay, so and it also correlates very well with like physical reality. So if this model stands up or doesn't stand up, you can be very sure that like the bigger one is likely to fall and kill people. But like if you somehow manage to make it stand without glue, obviously, these become not just a representational model, but you can literally begin to scale this. Like, so if you scale the geometry up, you can also imagine the forces are going to be scaled up in at least a quadratic or cubic way. So that's like also physical intuition, like, and you can correlate like physical behavior with like geometric quantities a whole lot more easily than like physical behavior with color, like, and or physical behavior with numbers. So that's again like, this is again collaborative work with like Block Research Group and Zaha Hadid Architects, like that we're trying to extend this things that we do in workshops, like the DLAB and etc. It's not just one-way traffic, so we take those ideas and like kind of try and scale them up, like add to that like our magic sauce, and kind of, you know, hope to construct some of these things in the near future. Again, it's meant to be only compression and like made out of stone without much reinforcement. But whilst we do that, like we try to apply similar ideas to make a small chair in stone and carbon reinforcement. So the black areas are where there's more tension in the shape, and so you put reinforcement, and the white areas where the stone, that's where are more compressive, let's say. I mean, it's not exactly a mapping one-to-one, but general idea. Again, we're trying to combine like some of the furniture ideas from Wagner and like with like the structural ideas from Block Research Group, and then also craftsmanship in Italy and Switzerland, like to kind of produce some of these shapes. So it's digital, but it's also handicraft in that sense, or traditional craft, and also CNC milling. Digital fabrication doesn't necessarily, or usually always means there's a whole lot of more manual work. And it's a similar story with like this thing, 3D printing on top of like a kind of hot wire cut mold. Start to finish, this was like about maybe 6 weeks, designing, making, to installing. And again, there were two startups that collaborated here. One was in Denmark called Odico, that does, the only thing they do is use a hot wire cutter mounted on a robot to cut foam. And then AI Build, which is a startup here in London, like they print in plastic, again, mounting an extruder onto a robot, and they print. So when we decided that these two companies should collaborate. They had never known of each other. And so we designed this piece so that we can enable that collaboration. So on the one hand, the base geometry on which the printing happens is hot wire cuttable, meaning it's made of straight lines. And then obviously you have to stack all of these pieces together and so on and so forth. And on the other hand, like the curly geometry is more adherent or more conducive for printing, because printers don't want to start and stop, especially if they're mounted on a robot. So you want the path to be as continuous as possible. So all we did was make this little simulation game of like pushing wire into a contained volume, and so it naturally has to curl. And so we did that digitally, and then if you can do it on a flat piece of box, you can also do it on a curved box, which is the diagram on the bottom, which says you take whatever is happening on the flat region, you just map it onto the curved regions. And then the robot can it rotates the drum, then it just prints. And there's a video at the end of this, so you'll see the more details of it like that. So here's everything taped up, and print and things printed. Similar story with like another favorite topic of ours is like curved origami, very related cousin of like straight line prismatic origami. And again, this has like a deep history, like, and architecturally, one of the interesting aspects of this was it was taught in the Bauhaus, as there was a textbook, a little textbook of like folding these kind of shapes. The black and white one, and then like mathematicians and artists in MIT and elsewhere have begun to pick this up now, and then there was also another topic, another feature that is underlying most of our work is that like many people are interested in these kind of topics. It's like on the one hand there are mathematicians, like this bearded guy. Who is more known for compression algorithms that go on to CDs and stuff, like, but he was interested in origami and he's made seminal contributions to that. David Huffman and also artists like Ron Resch, they also made like seminal contributions to the field. So again, it's already collaborative knowledge and historic knowledge. So it's one of the aspects that interests us. Like similar to shell structures, curved origami is another topic which shares these kind of features. Plus, there's increasing interest in the computational recreation of this and like the mathematics behind it, and so on and so forth. But at the base of it, it's like very, very designer intuitive. Like it's so simple that you just cut paper and like score it, and then you fold and you get like really curvature for free. On top of it, like you get like the entire design space for free. Like, so it's like a massive. So design then, as I said, like becomes like which of these do you choose and how do you choose that? Like you kind of have a directed search through design space. And like for two years, we used to run this workshop in the DRL. Students just did this 2D to 3D conversion manually, like draw on 2D and fold on paper. And then if you can fold in paper, you can scale up to acetate, metal, so on and so forth. So they used to do lots and lots and lots of these little paper models, and then like one day they suddenly start scaling up. But this is the process you do in 2D and then you fold. Right, and it is extraordinarily surprising, this entire piece, like rocking chair that one of the teams did, like it comes from one single piece of paper or plastic or any flat sheet there. But the real bigger scale one obviously had to be joined together by folding half of it, because the laser cutter couldn't accommodate like a 3-meter sheet. As I said, like, and then we did the exact same 2D to 3D, hardly anything digital here. We explored this in paper on physically, and then like we literally measured what was in paper and scaled up the 2D drawing, and that's how we produce a big 3D thing. Like by scaling up the 2D drawing. Like, so there wasn't a digital representation of this until very late. So almost all production drawings were like just scaled up like manual drawings, like, and cleaned up a little bit in Rhino and AutoCAD. So again, built in India with just a laser cutter and like 35 students, built over or made over like 3 to 4 hours each for each of these eggs, and that's what I did my MPhil on, like to try and understand somewhat geometrically what's going on, or how do you understand curved origami, and so the basic principle again is very geometric. There's a lot of physics, but it's physics abstracted into geometric conditions. The only two conditions you need to be making curved origami is that the strips, they need to be flat. So all the gray strips here, each of the squares need to be flat. They cannot be twisted. And where the squares meet, all the angles around that vertex need to add up to 360, meaning you can flatten it. So these are only two geometric conditions. Notice there are no crazy physics calculations here. And with a little bit of programming, you can ensure, again, by moving points, that these conditions are true, that like all the faces are flat and all the vertices, the angles add up to 360. So the key idea, move points until certain conditions are met, and in this case, the conditions are these two geometric conditions. And you can see that as soon as those conditions are met, like it unfolds perfectly. And then like you can produce all the nuts and bolts and like, you know, get your minions to make it and so on and so forth. So it's, and again, like you can do it in paper and like do a smaller one, like, and in this case, like we did this slightly more complicated process because like we had to simultaneously unfold 400 panels and make sure that the boundaries align. Like, so you couldn't unfold it once because then the next one is going to be affected. So you had to simultaneously ensure that all 400 panels are have these conditions, that like the faces are flat and the vertices, all those pink points, that the angles add up to 360. And so that's the difference between the pink ones and the gray ones, that like when it says perturb G equal to 0 means move the points until Gaussian curvature or the angles add up to 0. And the rest is unfold, you check for things match and like production things, and then we folded that, this time with like 80% of the panels were folded by a robot, 20% was too big for a robot, so we needed like smaller human hands, and then they were all bolted together. This was for the 2012 Venice Biennale. Yeah. Okay, so continuing on with this idea of flat sheet material, like, so this is already 4 years after 2012, like all of these curved parts are actually produced from flat sheet material. And inside these are like standard aluminum box sections. And from our side, this entire project was like about 3 months. And there was like literally one person working on it at any given time. So that's how much profession has progressed. Like all the previous ones used to take like 5 of us and like, you know, working for months and so on and so forth. Like by now, there's so much knowledge in the community and so many tools that like you can really see that digital fabrication is coming of age, and becoming more mainstream. Again, the principles are similar, like you somehow generate whatever design process you use, you generate a net of points and lines, and then in this case, move the points until all the beams are torsion free or until they're not twisted. So you will see that. So here's the points and lines version, or the mesh version of that geometry. And pink means lots of twist, and you will see that you move them a little bit, and these are like literally centimeters moving. Some of the points barely move, and already ensures that everything is green. And once that is true, you can literally make everything that is based on that underlying geometry is developable, and if it's developable, then you can unfold it, then you can use a laser cutter to skin the structure, let's say. So that in general, that's the idea. And yeah, here's, I don't know how many number of panels unfolded. So again, to say like little bits of moving of points makes the left side of our geometry, which we call, that's our designer's job, it ensures that like everything on the right side, like downstream construction and fabrication and shop drawings, everything, it becomes so much more simpler, like infinitely simpler, because like the left side is ever so slightly different from your initial like random or whatever arbitrarily drawn geometry. So in that sense, it has fabrication rationality embedded in the geometry, and therefore ensures that the downstream processes are more smooth and more easy to do. If we hadn't done that moving of points, the right side, everything would be like super twisted, and the budget would be going through the roof, because everything had to be then made custom and so on and so forth. So you can see how the profession is progressing from making everything custom to just changing the design ever so slightly. So we are incorporating a lot of the downstream construction aspects already upstream. Yeah, as I said, digital fabrication always means lots of manual labor. In this case, they're welding and grinding some of the pieces. Similar to 3D printing, this is, I will end with this research topic, which this is part of my PhD that I'm pursuing again with Block Research Group. Again, with the idea that like, how do you understand 3D printing, especially printing in concrete and clay, in a kind of intuitive way? So how do you generate shapes? How do you generate shapes that are 3D printable or highlight 3D printing capacities? And how do you understand how material behaves when it is 3D printed? So one of the main intuitions here is that like if you scale down masonry structures, earth structures, unreinforced masonry, if you scale them down, you can perhaps begin to understand intuitively how 3D printing works. Not plastic 3D printing, but like printing in clay and compression dominant material. So that's a general intuition. So you scale down and make the bricks a little bit squishy virtually in the digital space, and you get some kind of idea. So that's the idea here. Like the physics of two rigid bodies meeting is like well studied for both computationally and also in general physics. To that, like you just make the bricks a little bit squishy, and if you can understand the relationship between two bricks, you can understand the relationship between two rows of bricks, and once you can understand relationship between two rows of bricks, you can then begin to understand relationship between multiple rows, which in many ways is what is 3D printing, right? It's always layer by layer. Yeah, so that's the structural or physical side of things, and then there's also how do you create those layers. The typical 3D printing process is this: you model some arbitrary shape, and then you cut it up. You take it to slicer, Cura, whatever. So, but like the printer only cares about the path. Like, so you have gone through this like weird process of generating some shape and then cutting it up, and you don't even know where that line is gonna be on your geometry because it's in another piece of software, and like you're not actively visualizing these lines. So the second intuition is how do you generate shapes layer by layer? So to inverse this process where the geometry is, you build the geometry in layers. So you highlight or emphasize, so the overall geometry is implicit, and you make explicit all the paths. What is called the task graph is the path that the robot or the machine will follow. You make that visible to the designer and make it visible in the design process, not as an after process. And the one intuition here is like we can represent those paths as boundaries of images. Like in Photoshop, when you do find edges, you can literally use that algorithm to represent the entire piece of geometry like a CD scan as a stack of images. And when you want the paths, or when you want to show the paths, like you only find the edges of that image. And this has several advantages, and I will only go through one. One of the main advantages is that you can blend in images. And you can literally use Photoshop to design 3D geometry because it's very easy to blend images, as you know, and it's much harder to blend like a geometry of a rabbit with a torus, for example, right? Like, and that's very hard to do in meshes. It's super easy to do in images. So we choose to use image representation and not mesh representation for this reason. And then we highlight the layers because that's what designers should be aware of, like the relationship between layers. And that's so, and then you can begin to literally design all kinds of complex geometries by keeping track of how the layers evolve from one layer to another. So one circle becomes two, and like so on and so forth. So you can see here, all you have to specify is the start and end, and you do the blending in image space or as images, and the curves are doing their thing, and then you get like these. This is rather hard to do. You can definitely model this in meshes, but it's almost trivial to do with images. So you just blend the image on the left, F to G, and the geometry evolves from A to E. And so you can see like this has several advantages. So you only have to specify the top as 3 circles and the bottom as 2 circles, and everything else in between becomes a natural consequence of blending from one image to another. And then once the process is so simple, you can like really like explore a wide range of like shapes that make it which highlight one of the key capacities of 3D printing. Even though it's layer by layer, like you can like do all of these complex geometries and complex topologies. So each of these 3D prints is basically represented by 2 images, one on the top, one on the bottom, and everything else is like a blend, interpolation between them. Okay, so to conclude, a large part of like our research is in the physical, but also to abstract the physical into geometry, so that it becomes amenable, a vehicle for us to collaborate with engineers, with mathematicians, with clients, because everyone understands geometry, or more people understand geometry and than they understand physics. So if you can like then abstract physics into geometric properties like of curvature, of light, how light bounces off, reflectance, these are all geometric properties, then everyone can have a say, and then that's so that provides the substrate or the kind of technologies for our next phase to really bring consumers into the design process. So by already rehearsing all of these geometric-based language, so if you remember the Eames diagram, over the last decade, like we have tried to rehearse like a vocabulary of materials and techniques and how to make things, and we built our collaborative network to be able to design freely. Again, not to disregard all the BIM stuff and all the other usual aspects of delivery. We have a separate team doing that. These are very, very important aspects of construction, but we are more focused on the early part of design and how that can, all of these complexities can be somewhat abstracted early on in the design process. So this is generally, we are very optimistic for the future, because every year we see these kind of pavilions like get bigger and bigger and bigger, and more people in the world are doing these kind of things. Including you, who you might put up something at the end of DLAB outside, like and this is the status quo, and we also think our contribution to this is this little gallery for mathematics that we did in the Science Museum in London, where again all of the things that that has been rehearsed, we have tried to suppress that a little bit too. So everything you see in this image is some application of all the research things that we had done. So for example, the benches were hot wire cut, the fabric stuff is like a kind of tensile structure. We also studied how to put these seam layouts. You can't like randomly put seam layouts wherever you want. Otherwise the fabric will wrinkle. So all of these things was feasible with a very small team in a very small time budget. The entire design phase was like maybe 2 months, and then like start to finish was maybe 16 months. It's a small gallery, but like there are over 200 objects, so in the next phase, we want to pay more and more attention to the people and less so we want to take for granted that like we already know. I mean, of course, that research is going to continue, like in the discipline and domain, but we're slowly trying to shift focus to begin to understand equally computationally and equally rationally why are these two people standing there? Why not over there? You can begin to leverage some of the same kind of thinking and technologies from other disciplines, some of the math from social science and data science and AI and other things. You can begin to leverage to study equally computationally and equally rigorously what the user experience of spaces is likely to be and how you can maximize that. So that's a general outlook, let's say. So with that, I will stop here and I will play a video for you. Thank you very much. Where's the video? And if you have questions, I can take them. This trick of playing a video I learned like a few years ago, so there's no questions and I'll quietly escape. Again, maybe across all these videos, you will see that almost all projects at some stage will involve the strategy of moving points. You start somewhere nearby and then move it until you're happy, and then you start again. So it's I mean, I'm kind of trivializing all of the several communities of knowledge that is coming together and is evolving, but I just want to give you an intuition about it, and I don't want to try and trivialize lots and lots of people's work. For the more technical bits, and especially the structural bits, as I said, you should watch or come to the lecture by Chris Williams. The previous project, it was literally us doing the manual fabrication in 40-degree heat in Venice. We were climbing up there, putting bolts. So for those of you who think that people in Zaha have an infinite budget, actually not. We are genuinely interested in this, and so we put our put our efforts on the line to see some of these things through. It's not that somehow magically people throw money at us, that doesn't happen to you, it doesn't happen to us, it doesn't happen ever. Also, this one, it was literally everyone from the three teams, AI Build, Odico, and Code, literally putting their physical effort apart from machines and programming things, and just because it was genuinely interesting to and exciting to do this. Not because it was some kind of scientific demonstration, right? It was just a joy. It was fun to collaborate and then try and do something, and this has become one of the most popular pieces in our exhibitions almost entirely by accident, because we had no idea what's gonna, in all these projects we had no idea that like if things will actually materialize. So we almost go into all of these projects like not knowing how to produce things, and then relying on risk taking, but like calculated risks. And like early on, like we build a collaborative team, and we know amongst the team, like there has to be the necessary knowledge to actually physically realize this and design these kind of things well. So it's not that like, you know, we already have all of this knowledge and then we're applying it. We use these projects to generate knowledge. Like, so by taking risk, trying to do like what is usually not or considered undoable or like too expensive, you're forcing people to collaborate and be clever. And that's the key message I want to convey, that like if you understand things geometrically, many people can communicate, and you build a collaborative team first, and the results will follow. So with your DLAB efforts, I would say that's what you should take away the most, apart from knowing how to move some sliders. You know, yeah. That's important too. But yeah. Thank you. Okay. Yeah.
Sorry. Thank you for that. What we've seen today is quite interesting. But my question is, when we apply this to an architectural scale, I still haven't seen the relationship with the context. I'm saying this because I'm from Saudi Arabia.
Yep.
I'm in Riyadh, and Zaha Hadid has 3 projects there,
Yep.
and a million other architects. And our problem is that every building is becoming an iconic building. Mm-hmm. So we have a visual clutter.
Yeah.
I mean, they're lovely buildings, but they don't come together.
Yeah, you should give all the buildings to us. So you won't have clutter. No, but fair point that, as I said, like there was by definition and a necessity that like all of this technology and the technical aspects are not trivial. So the discipline and the profession and various aspects have to come together to begin to address the more true concerns of architecture, like which is how does architecture, how do consumers of architecture, how they can be participating in the production. And so we can then actually produce what they want, rather than kind of just telling them this is how it's produced. So that's why I said that like these kind of deliberate suspension of disbelief or period of focused endeavors and efforts across the world, not just in one architecture firm, but like in academia, and collaborative and cumulative ways of working is a necessary step towards actually addressing all of these other concerns. So now so we are saying social concerns, but like, or social value propositions, but like engineers are equally looking at saying, okay, now we have understood all the math, or enough of the math, enough of the material behavior, like can we now make it more environmentally sustainable? Like so it's now beginning, we think that we should begin to address these other concerns, and they might relate to context, and some might relate to environment, some might relate to cultural context, some might relate to communal context, and so on and so forth. So give us a few more buildings and wait a few more years. That's my answer.
Thank you. I have another question if you want.
Okay. All right. Thank you.
Thank you.
you.